start with a quick recap about coordinate systems and degrees of freedom. There are 6 degrees of freedom in the world. You can best visualize this with an airplane that can move back and forth, move left and right, up and down, which are 3 degrees of freedom, and then rotate around each of these axes, which is commonly known as pitch, yaw, and roll. We also introduced the right-hand rule, which is a good way to memorize the relative orientation of the coordinate axis and their direction. Essentially, you take your right hand and align it with the x-axis and the y-axis, and then your middle finger gives you the direction of z. There's a second right-hand rule, which is using your hand and cusping it around the coordinate axis so that your thumb is pointing in the direction of the coordinate axis, and now the direction of your fingers will give you the positive direction of rotation. In order to represent pose, we talked about that you not only need a vector that points toward the center of gravity of the object, but also an entire coordinate system that is mounted at the center of gravity and gives you the orientation of your robot. When I say a coordinate system, I want you to remember that each point in 3D is actually a linear combination of basis vectors. In the simplest case, the basis vectors are actually 1, 0, 0 for x, 0, 1, 0 for y, and 0, 0, 1 for z. And each is multiplied with a coefficient, and so together this gives you a vector. There are different ways to represent this. When you write down the basis vectors and the coefficients like that, you can also write them in matrix notation. And now I'm plugging in the normal basis vectors for x, y, and z. And so you see that there's actually what we call a rotation matrix that takes 3 coefficients and turns them into a point. In this case, the rotation matrix is the identity, so it actually doesn't do anything. I just recall this concept to you because today we will talk about rotation matrices in more depth. When you have the rotation matrix, it has 9 values. I also convinced you that you only need 4 values to represent orientation, because when you have a rotation matrix, a third vector is always given by the other 2 being orthogonal, and the third value in each vector is also given because all of them have length 1. This is why you can get away with only 4 values, which Robotics does when it uses axis angle or quaternion notation, which is something we will talk about later in this course. Finally, we derive the forward kinematics equations for a simple differential wheel robot, where the forward motion is given by the rotations of the left and the right wheel, and as well as the rotation around the z-axis. Today we will talk about coordinate transforms and odometry. For this, I want you to consider the I.5 robot in a Robotics environment. And you see here 2 coordinate systems. One is the world coordinate system, which I indicate with a little w, and another coordinate system, which is the robot coordinate system, for which I put a little r. You can see that one is rotated to the other. In this case, the rotation angle is around 130 degrees. You can better see this when I rotate it only by 90 degrees. So you see now there's a 90-degree rotation that the robot has done, turning away from the start line toward the line on the ground. When you look at it from above, you see this more clearly. There is this 130-degree angle, and there are 2 coordinate systems which are rotated from each other. Now, for simplicity, let's not use 130 degrees, but actually look at a much smaller angle, like 45 degrees, where you can see more clearly how to derive the math. Now, what we're interested in, we are having a point P, which is in the robot coordinate system. That is, it has 2 components here. Let's forget about the z component, which is 0. One of them is the x-axis, and the other one is the y-axis contribution in the robot coordinate system. At the same time, we do have a world coordinate system that also can see this point, and we would be interested in the coordinates of this point in the world coordinate system. That is, we are interested in this point here, where the point intersects the x-axis of the world, and this point here, which is where this point intersects the y-axis of the world. Now, using the concept of a rotation matrix, I'm interested in some kind of mechanism that allows me to multiply the point in the robot coordinate system and get the point in the world coordinate system. So one way to do this is to do very basic geometry. In this case, I reason about this by looking at all of these intersecting lines, and I do see that I would need to compute this point here, and then I subtract that line from it to compute this point here. Now, if you look at this triangle here, I can look at the hypotenuse length here, which is the XR component of this point. I know the angle alpha that this triangle has, and I know the length of the adjacent that I'm actually looking for. So I can write down that the cosine of alpha is the hypotenuse divided by the adjacent that I'm looking for. Now I can reformulate this, bring this over, and so I'm getting an expression for x1 w, where w indicates the world coordinate system. I put a little 1 here because this is just one component of this point that I'm looking for. In order to compute xw, I need to subtract the blue part, which I can again do by looking at this triangle, which again has an angle alpha here, and it has the hypotenuse being the YR component of the robot. So now I have the full equation. It's cosine of alpha times the x component in robot coordinate system minus sine alpha times the y component in robot coordinate system. I already told you I'm looking for some kind of matrix to compute x, y, and z. So this looks like this. I have the matrix now here. It has 3 components. The first line takes the x and the y from the robot coordinate system. Now, in order to get the second row, I can do very similar operations. I'm looking for the point where this point intersects the y coordinate of the world frame, and I can apply very similar reasoning, adding this time 2 components together to get the point on the y-axis. Now, in the last row, z, I don't do anything. I essentially take over the z dimension from the robot coordinate system and move it forward. Now, this is very cumbersome. There's an easier way to do this. And when you look at this matrix more carefully, you will see that when alpha is 0, that is, the 2 coordinate systems are together, this matrix actually becomes the identity matrix. So cosine of alpha with alpha being 0 is 1, so you have 2 1s here, while sine of alpha is 0, so you have 2 zeros there. Now, if I start increasing alpha by a tiny bit, you will see that I don't have 1 0 0 anymore for the x, but I have a projection. And in order to compute this projection, I can simply project the x-axis of the robot coordinate system to all of the x's in the world coordinate system. And one way of doing that is using the dot product. Now, the dot product is defined as the cosine of alpha, which is the angle in between 2 vectors, times their length. Now, the length of these vectors is always 1, which is very convenient. So I can drop this here and essentially just plug in the cosine of the angle in between them. All right, what's the angle between xr and xw? It's alpha, so I plug in cosine of alpha. What is the angle between xr and yw? Well, this angle is 90 degrees minus alpha. So I plug in cosine of 90 minus alpha here. Now I can look up the cosine and sine identities, and I find that cosine of 90 degrees minus alpha is sine of alpha. So I put this in here. Now let's do the third step and project xr onto ZW. The angle between those two is always 90 degrees, so cosine of 90 degrees is always 0, so I put a 0 here. I can do the same for this equation here. YR times YW is again the cosine of alpha, so easy. Now I look at YR and XW, so YR and XW, and I get the cosine of 90 plus alpha. Again, I can look up the identity and I find that is minus sine of alpha. The good thing about this is that it always works, and we will do a little exercise. Okay, here we have three coordinate systems that are labeled S, B, and C, and as you can see, they're all rotated from each other. Now I give you one of those rotation matrices which rotates the Z coordinate system into the S coordinate system. We can go by the book and use the dot product notation and start with x of C, and project it onto x of S. The angle is 90 degrees, so cosine of 90 is 0. Now we do Cx on Sy. The angle is again 0, and we put down 90 degrees, so we put down a 0. Finally, we project Cx onto Sc. Now the angle is 0 degrees, and we put down the cosine of 0, which is 1. Now the next column, we take the y-axis of this coordinate system C and we project it onto x. The angle is 180 degrees. The cosine of 180 degrees is minus 1. The other two angles are 90 degrees, so we put in a 0. The third column, we look at Z. We project it onto x, 90 degrees, 0. We project it onto y, 180 degrees, minus 1. And we project it onto Z, 90 degrees, so 0. Now what happens when I take a point in C? Let's take the point 1, 0, 0. This point is around here. It goes 1 up the x-axis and 0 the y and z axis. What is this point if we had the same coordinate system, the same position here? What would happen if you look at the same point, but we want to know how it looks in S? Well, in S, this would be a 0, 0, 1, because this point would be exactly here. It would go up 1 and 0 to the left and the right. So let's verify this. Let's plug in the point 1, 0, 0 and run it through this rotation matrix, which is transforming coordinates in C to coordinates in S. 0 times 1 is 0, minus 1 times 0 is 0, 0 times 0 is 0, so we have zeros here, and we only get a 1 at the very end when we take the last row and multiply 1, 0, 0 with 1, 0, 0. So this works. The next thing we can do is we can look at a third coordinate system and bridging from S to C and from the next thing we can do is we can go backwards and look what happens when we not go from C to S, but from S to C. And now I can do the same math. I look at the x-axis of S and project it onto the x-axis of C and so on. But I can also very quickly see that these matrices are very related. They are in fact the transpose. So the transpose of this is that. And so you see here 0, minus 1, 0. You get that here in the column. The second row is the second column here, and the third row is the third row here. This can be done because these matrices are rotation matrices and they are orthonormal, and there the inverse is essentially the transpose. Now let's look at a third coordinate system, which is the coordinate system B. I can write down rotation matrices to go from B to S and from C to B. And now I can compute the rotation matrix from C to S by multiplying them together. And here you see this is very convenient. The B's essentially cancel each other out, and I get the rotation matrix from C to S by simply rotating them. Rotating two matrices, I take this row and multiply it with this column, and then this row with that column, the same row with that column, and then I go to the next row and so on. And what do I get is exactly the rotation matrix from C to S. In robotics, we not just have rotations, but also translations. And you can see that if you want to think about how to turn a robot motion here in red into the corresponding motion in the world coordinate system. In this case, I label this Q, which is given by the wheel speed and the radius of the wheels. So this has been delta x before. I'm now using Q here in order to match this standard notation. And what I have to do is I have to first rotate it and express it in the coordinate system A. So this is the coordinate system B, the robot coordinate system, but I want to know what happens in the coordinate system A. So the question is, what does this vector mean in the world coordinate system? In the robot coordinate system, it has been something like only along X, but 0 along Y. In the world coordinate system, it will have both an X, or in this case a Z, and an X component. So I need to perform the rotation from the coordinate system B to the coordinate system A using the rotation matrix, but then I also have to add the translation vector that gives me the root of the coordinate system B, and which should be provided in the coordinate system A. So the first thing I need to do is I have to express the vector in coordinate system B in the coordinate system A by rotating it, and secondly I have to add the base vector. With this I can come up with an equation to turn the delta x of my robot into a motion in world space. For that I take the rotation matrix and then I add the previous position of the robot in the world and add them up as we have done before, and with that I get not only an odometer but a complete localization solution that allows me to compute the location of the robot as it moves in the world. Here we note that the angle is simply given by adding the rotation angle up. This is possible because the z-axis of both coordinate systems is aligned. They are both pointing in the same direction. That is, they have the same direction of positive rotation. And when the robot turns left in its own coordinate system, it will also turn left in the world and so on. So I can just add these up, and then I use the new alpha in the world coordinate system when I compute my rotation. Now you might ask, why do we actually have to add these motions up? When you consider a robotic arm, I know where the robot end effector is at all times by just looking at the angle of the motors. Why can't I do the same thing with a differential wheel robot? Simply look at how much I turned each of the motors and from that infer where the robot is. So in order to understand the difference, let's look at what we call the configuration space of a robot. And in this case, I have a robot with 2 degrees of freedom, which has 2 angles. And for now, just consider this robot arm here, which has 2 degrees of freedom, and use the values on the x-axis and the y-axis to compute its position. So we start at 0, 0. That means the robot is probably in a straight line. And then we increase the angle of both of these motors by pi to 2 pi and 3 pi, which makes the robot move. So this whole thing moves over some way. And then we start moving only one of those motors back. And so we perform a closed loop in the configuration space and end up back at 0, 0. Where's the robot then? Well, it's at the same position where it started from. That means the closed loop in the configuration space is a closed loop in the Cartesian space as well. This is not the case when you use these rotations for the left wheel and the right wheel of a differential wheel robot. And I let you watch a little video that is also on Coursera, which shows that in Robots. But just think about it real quick. The robot will drive somewhere and then it will perform a couple of turns. and then it will unwind its wheels to be back at 0, 0, but it will not return to the original position. That is, its trajectory in Cartesian space is not a closed loop, even though it has been a closed loop in the configuration space. In this case, we call the platform non-holonomic. Robots where this is the case, we call holonomic instead. And examples for this are all or most robot arms, or a robot that is sliding on a track like a train. As soon as the robot has wheels, it becomes complicated. A unicycle is not holonomic because it can turn on the spot, it can move back and forth, and it can end up anywhere in the space depending on the sequence of actions that it takes. A unicycle on a rope instead is holonomic. It can only go back and forth on the rope, and thereby the wheel position always determines where the robot is. All right, in summary, we introduced the concept of rotation matrices, which are the basis vectors of the coordinate system that is projected in another coordinate system. I can use this rotation matrix to project entire vectors and convert them from one coordinate system into the other. I can construct these rotation matrices element-wise by projecting one axis each from one coordinate system onto the other. And finally, we introduce the concept of holonomy, which are robots where closed loops in joint space result in closed loops in Cartesian space. Now, there are a couple of video snippets on Coursera which provide condensed snippets that help you to understand some of these concepts better. We will also work on turning the odometer readings from last module into world coordinates to localize your robot in the arena. There is a homework to do, which is the final exam for this course. And here, pay some attention. The honor section is not mandatory, but the final exam will have questions from the honors examen. So I recommend you to go back and review all the previous quizzes as well as the lecture materials until you thoroughly understand everything, and then go and take the final exam.